Okay, so let me again recall the most important things I said in the last lectures. Okay, what you should always recall is the OPE between J and itself, and it is equivalent to writing down this mode commutation relation. And this form is usually called current algebra, and this form is usually called Afan-Kac-Moody algebra. And then we showed that you can canonically construct an energy momentum tensor, which is the bilinear normal ordered product of the currents with themselves. And you have to put a funny normalization constant in front, which was this gamma, which turned out to be 1/2k plus the dual-Coxeter number. And the dual-Coxeter number is just a number, but recall maybe for SUN is just n. That's the main example I will need. And this T satisfies the Virasoro algebra, and the central charge turned out to be this formula. Good, and then in the very end, we showed, or I convinced you, that SON at level 1 is something special, and we constructed it in terms of n free fermions. So it was a free field theory in disguise. But in general, for general level, you won't have such a thing. We had something similar for UN level 1. Okay, so let's go on. And let's do the same thing that Sylvain did in his first lecture with the Virasoro algebra. So let's talk about representations. So this is essentially all the same things, but just in this Afan-Kac-Moody setting. And as he did, I will also work now in this mode language. So I will have to define what do I mean by a primary field now. So a primary field for me is not a Virasoro primary field, but it's something stronger, because I want it to be primary also about, with respect to this bigger current algebra, which contains the Virasoro algebra. So I will call my primary field lambda. So he called it V, but it's the same thing. And again, I want the energy to be bounded from below. So I want essentially the same things he wanted. And okay, so I want that all positive Ln modes annihilate this state. In particular, it should be Virasoro primary. But now I want something more. I want that all positive current modes annihilate the state. So I want this to be 0 for all n bigger than 0. Okay? Good. I want something slightly more. He also said, okay, so analogy was this is 0 for all n bigger than 0. So, and then he also had the condition that L0 on V could be whatever eigenvalue you wanted, the conform weight, delta. Okay? So now I have several zero modes. The zero modes, they just satisfy the usual algebra, our Lie algebra we started with. So they have commutation relations like so. So that just means that my zero modes, they should form a representation on this lambda. So the natural condition I can put that this lambda is actually a highest weight of a highest weight representation with respect to the zero mode algebra. So I also want that lambda is a highest weight state with respect to the zero mode algebra. If you don't know or are no longer particularly sure what highest weight state for Lie algebra representation meant, just think in terms of SU2. I will write down explicitly in a moment what it means for SU2. And also most of the representation theory I will just discuss for SU2 and mention how it generalizes for general algebras. Okay, so let's go to SU2. So that's just one example. And let's write down the commutation relations explicitly. So we will have a 3. I will go to the 3 plus minus basis. So there are 3 oscillators like that, J3, J plus, J minus. And okay, let's write down explicitly what this is to fix our conventions. Okay, the 3 with plus, the invariant form, 2 form will vanish, okay, because they're not the same. So this is actually J plus M plus N. There's just a structure constant, which is 1, because this is the plus. I can also put the minus, then I get a minus here in front. Okay? So I should maybe say something, because till now I always assumed that I'm in this basis, which I called AB, where the 2 form, the central term, just takes the form delta AB. And because this was convenient for shuffling around indices. What I will do now is not in this basis. So this 3 plus minus basis is not of the form that this 2 form, this kappa AB we introduced in the very beginning, is just delta AB. Okay? This would be the basis you know of SU2, the J1, 2, 3 basis, and then you introduce plus by J1 plus I, J2, which is the raising operator and the lowering operator. Okay, so this is a different basis. And here, so the 3 with 3 commute, but they have now a central term, which in this normalization is K half, but there's no FABC term here. And finally, we have the J plus with J minus. And they have a central term as well as a non-central term, which is 2J3. Okay? So that's one way of writing SU2 algebra. And pluses with pluses all commute, minuses with minuses all commute. So I see some confused faces. Is everything all right? Okay. So that's just my choice of basis. So now let's write down what it means, this condition in that case. So it means that J3 or plus or minus, I just write collectively like this, is 0 for m bigger than 0. And let me give, in this case, another name. I call lambda L. You will see in a second why. Because the 0, so this L should be a highest weight state of my SU2 representations. And you know that SU2 representations are just labeled by their spin. So this L is just my spin. So I want that J plus of L is 0, because it's the highest weight state, and J3 of L is LL. And J minus of L generates me the other states in the SU2 representation. Okay, in general, this lambda is, you can think in terms of Dünken labels, if you know what that is. So, but it's just some labels to describe the highest weight state. And sorry, I forgot the 0 here. Okay. And as Sylvain did, let's introduce a Verma module. So the Verma module, okay, I can maybe add an index L. It's obtained by acting with all so I've constrained what should be the positive mode operators on that L. I've constrained what is the 3 and plus of the 0 mode. So I can act with all the other operators as many times as I want, and I generate my Verma module. So let's write this out one time. So I can act with that, any number I want. So everything I'm writing here is just meaning I can act many times. I can act with the -1 modes as many times as I want. I can act with this mode as many times as I want. I can act with this mode as many times as I want. I can act with the 0 minus mode as many times as I want. I put the 0 somewhere, and I act on L. And all these integers, ni plus minus and ni3, they're all bigger or equal than 0. So I just generate all possible descendants. That's what we did for the Virasoro algebra. Right? We took the highest weight state, we acted with all L-1s as often as we wanted, L-2s, and so on. Okay. So, and also exactly the same as in the Virasoro algebra, that is the generic case. So our generic representation is described by a Verma module, just labeled by the spin L. However, most of these Verma modules have null vectors, or singular vectors, which again is the same thing, which means these are vectors which are again primary fields. So some of the vectors which appear here might again be primary fields. And there's sort of one stupid one, which you probably know. So if I take the J0 minus, and I act 2L plus 1 times on L, then I will just run down in my global SU2 representation until I hit 0. So if I get 2L times down, then I have the lowest weight state. If I put it one more, then this is 0. Yes.
So here it seems that you're acting with all generators, no? You can eliminate some of them just by computation.
No, because so those commute actually all of, I mean, they don't commute, but it's like in the Verasoro algebra. You take an ordered basis. So if you would commute this, so I fix the order here of the generators I want. So if you would take commutators, you would destroy the order. So there's only one way of writing it in this order. So this is the Poincare-Birkhoff-Witt basis, if you like. Yes?
If instead of SU2 I have a different Lie algebra, I should do something very similar using the Chevalier or
Yeah.
basis, basically.
Yes, that's right. So basically what you would impose is that all Cartans on the highest weight state have some particular eigenvalue. The positive roots all annihilated, and the negative roots give you descendants in the global algebra. Yeah. Okay, so that is sort of the stupid null vector we always have in the Verma module, provided, of course, we take a valid SU2 spin. So we want our SU2 spins as always to be half integer, positive half integers. Then we have this null vector. But there's something interesting happening sometimes. So this is still not super interesting. Yes?
Why do we want the SU2 spin to be unlimited?
Good. If it's not half integer, then your SU2 representation, so the question was why do you want half integer? If you don't have it, then you would run down with your lowering operators to -infinity, and your representation would be non-unitary, which is something you might want to consider, but we want to consider unitary Wess-Zumino-Witten model.
So there will be a notion of unitarity also for these larger representations?
Yeah, let's write it down, because I will need it. So if I take the dagger of J plus dagger, I will get the J minus with -n. And so, okay, Sylvain didn't use the dagger, but I will use it. So the usual dagger on the Verasoro algebra, just for comparison, is L dagger, so L minus n. Okay, so the dagger always puts your n to -n. So if you want to compute norms of some descendants, so you put, for instance, let's just do Verasoro. So if you want to compute, the norm of this state, what you do is to sandwich it with itself. Then you have this, and the dagger puts you the -1 to a 1. And then you replace this by the commutator, because the L1 annihilates the primary state. And this gives you 2L0, which gives you 2 delta, assuming that V is normalized to 1. Okay, that's the way you can always compute the norm. And since I want something unitary, I want this norm to be always positive. You see, for standard Verasoro representations, this would tell you that the conformal weights you have in your theory should be all bigger or equal than 0. Okay, but yeah, it's something you don't necessarily want to require of your CFT. It's just an additional extra. But since we started with an action, we expect there only to be unitary representations. Good. So now, remember also that Sylvain had some additional null vectors, which were maybe not so obvious than this J0 minus acting many times in the primary state. He had some other null vectors which appeared at level RS, which were very complicated. And for Wess-Zumino-Witten models, the same thing happens. Unfortunately for us, the null vector is very easy to write down. So I claim that there is a further null vector, which is of this form. So we add k plus 1 minus 2L times on L. And I claim it's null. So, and let's do it. It's not a hard computation to show that this is indeed, again, a primary state, which is not obvious. Okay, so to show that it's a primary state, we have to show that it's annihilated by all positive modes. Okay? So, but it actually suffices to show that it's annihilated by the 1 modes. Because, for instance, if you know that it's annihilated by all J1 plus minus and 3, then you can just produce the higher modes by taking repeated commutators. So, for instance, the J I don't know, j3, 2, for instance, would be j plus 1, j minus, 1 minus with a half, I guess. So since those annihilate, this will also annihilate by recursion. So it suffices to show it for those. Then, and furthermore, we also should show J0 plus. So maybe let's just start with J0 plus. So if we act on this, it's very easy that this annihilates, because just by looking at our commutation relations, the J0 plus commutes with the J plus minus 1, because plus with plus always commutes. So this just goes through, hits L, but L was the highest weight state, so you get 0. So that's 0. Okay? Good. So that we have covered. Similarly, this is very easy because plus always commutes with plus. So the J1 just goes through, hits L, and gets 0. Okay? So let's increase the complexity. Let's act with J1, 3. So now it's not obvious that you get 0 because there's a non-trivial commutator. Okay, I can replace by the commutator because J1, 3 annihilates L. And now I just have a commutator of something repeated. So I can write it like this. I have a sum from M0 to K plus 1 minus 2L. Sorry, K minus 2L just. And I put M of those in front. So that's the usual way to compute repeated commutators, like that. And then I have remaining here K minus 2L minus M. Okay? And this, now I read, what is it? Okay, the 3 with the plus, there's no central term, but I get back the plus. So this one is J plus 0. Yes. But now the J plus 0, I can just commute through. Hits L, you get 0. Okay, because plus with plus always commutes. So this is still 0. So till now it looks good. But obviously I could have done this till now with any power of J minus 1 plus. So now the most interesting one is to look that this one annihilates it. And then we're done. Okay, so let's do the same trick as there. I have a repeated commutator. So M runs from 0 to K minus 2L, J minus 1 plus M. And here I have now J1 minus with J minus 1 plus. And I have the remaining one. K minus 2L minus M on L. Okay. I evaluate this. What is it? It has a central term, because the minus with plus gets a central term. And it is, the central term is k, because the mode number is 1. And then I get minus 2J03. Okay, there's a minus, because you should turn it around to match the definition there. Okay, and the J03 we can evaluate, because every one of those, so this here had J03 equal to L eigenvalue. Every plus operator puts me one more. So this on the state here is just K minus 2L plus K minus 2L minus M. Okay, the L is from the highest weight state, and then I applied this many pluses. So that's what I get. Okay, so let's write this slightly nicer. So how many L's do I have? Should be here minus L, so it's 2L in total, minus K plus 2M. Something like this. And now, okay, so now it's just an exercise in summing series, because now I have to sum from M equal to 0 to K minus 2L. So that's just Gaussian sum. I have this one, that's easy. Okay, so here there are K minus 2L plus 1 terms, because I have the 0 included. That's from this piece. And then I get this Gaussian sum, which is K minus 2L times K minus 2L plus 1 divided by 2 times 2. And if I'm very lucky, those two terms should cancel now. Okay, so they indeed cancel because that's the same term and this is the opposite term. So I get 0. But you see here I had to do a calculation. And this will only work with this exponent here, with this power. Okay, so we have a null vector. Good, it was very easy to write down and quite straightforward to check that we have such a null vector. Okay, so now, yes. Yes, I will come to this in just a second. Yes, good. So now you might say, okay, why do you care that you have this null vector or you don't have this null vector? Just some other representation. But in the context of unitary CFTs, you should care. And also, if you don't like unitary CFTs, also you should care, because Sylvain told you that every time you have a null vector, that's good, because this will restrict your fusion rules, and potentially you have the chance that this will end up with a rational CFT. So if you have a null vector, just go for it and try to put it in your theory. Okay, so, and just to say, why would you care about unitarity? So if you compute the norm actually of this, so that's an exercise where you should go through the same calculation again. So compute the norm of this. Now I put any exponent here. Then it turns out to be n from 1 to n, and then there's k plus 1 minus n minus 2l. Okay, so now let's think what this means. So indeed, if n is equal to this special value, this k plus 1 minus 2l, then the last term here, there will be 1 where this bracket is 0. Okay, if I put small n equal to big N, this is 0. So the norm is 0. So that, again, confirms our result. It has 0 norm, this state. And if we would go on, and there's this 0 somewhere, the norm will stay 0. Also, if we put more descendants, if we make this n bigger. But what if there's not a null vector? At some point, this product here will become negative, because the n becomes bigger, 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 bigger. At some point, there will be negative product here. So at some point, we would get a negative norm. If there's not, the only thing which can save us is that at some point we have 0, and then we have 0 forever. So if you want a unitary representation of this algebra, the only chance for you is to put this null vector into it. You want it. Okay. So let's see if we want it. That gives us a constraint. So we want null vector. And the constraint is that, first of all, this thing here should be an integer exponent. That's the most stupid thing I could say, but it's not a non-trivial constraint. The constraint is now that for this to be an integer exponent, I need that k is an integer, which somehow popped up now out of the representation theory. I mean, I did the same argument before in the action, and k turned out to be an integer in the action, but here we see the same conclusion from representation theory alone. So you have two different arguments now why k should be an integer. But there's another conclusion, because also this should appear at a positive level. If it doesn't appear at a positive level, if k plus 1 minus 2l is smaller than 0, smaller or equal than 0, then this is just doomed from the get-go, because it's already 0 at the first excitation. So I also want that k plus 1 minus 2l is at least 1. But that is equivalent of saying that the spin is bounded by k over 2. So there's the important conclusion that in SU2 Wess-Zumino-Witten model, your spin cannot get arbitrarily high. There's a bound on your spin. This is the spin of the ground state representation, of the zero mode representation. Of course, higher up in the Verma module, if you decompose with respect to your global SU2, you will get bigger spins. But of the ground state representation, there's this bound. Okay. Yeah, and this also has a generalization to other affine algebras. So here, you would, instead of the spin, you get the inner product of your Dynkin label, of your weight of the representation with the highest root, and it should be smaller or equal than k. So in any case, there are only finitely many representations. So that's maybe the most important conclusion. We have finitely many representations. And Sylvain told you a nice word for these kind of theories. If you have finitely many representations, these are rational CFTs. So we will construct here another rational CFT. You have learned about the minimum models now, and this will be another example.
So the fact that this rational CFT has something to do with some number being rational?
Yes. So you can show, the question was that why is it called rational CFT? Is there some rational number? And indeed, you can show that if your CFT is rational in that sense, it has only finitely many representations, then the central charge and as well as any conformal weight in the CFT is rational. That's where the name comes from. Good. So in general, just some terminology. So in general, I will write, I wrote these highest weight states as lambdas, and lambda runs over some set of allowed representations I will call R. Sugawara called S, but then there are too many S's, so I like R better. Good. And this set is finite, because we are dealing with rational CFTs. Good, so let us now connect. So this was the Affe-Katzmoody representation theory, at least in SU2. Let us connect it to the Virasoro representation theory. So lambda is also a Virasoro highest weight state. Okay? And what's its conformal weight, you can ask. So why is it the Virasoro highest weight state? Because if you compute ln on this, then this is normal ordered JA, n, and there's this gamma, which is 1 over 2k plus hv. And here, in this normal ordering, we till now had normal ordering mostly in terms of fields, but you can translate it in terms of modes. Maybe I do that, because it will appear in the exercises. Looks like that. So I could also put AB here, so they don't have to. So I have those sums, and now I have to tell you from where to where they run. And here I want to put the annihilation operators to the right. So I want the n index here to be negative, to be a creation operator, and this to be an annihilation operator, meaning that the mode number here should be more positive than this one. So the constraint, so what turns out to be the equivalent of this normal order prescription you have in terms of field is to require that n here is smaller equal to minus h, where h is the conformal weight of the field. So in this special case, it's 1.
So it would be m on the left-hand side.
Right, thank you very much. Okay, so that's the normal ordering prescription in terms of modes. And here, if you apply this, you see that if this n is bigger than 0, then my positive operator, j, will always be to the right, which kills the lambda here. So because here this one mode number is always positive to the right. So that's why I get 0 if n is bigger than 0. Okay, so in particular, these are also Virasoro highest weight states. But of course, there are Affe-Katzmoody descendants which are Virasoro primaries. So that's maybe you should convince yourself. For instance, this one is a Virasoro primary, but it's an Affe-Katzmoody descendant. So there will be many, many, many Virasoro primaries in the Verma module. Good. So, but of the lowest weight state lambda, what is its conformal weight? Good. So we have to evaluate this gamma, JA0 mode now. So of this, what is surviving of this definition? So as long as I have positive mode for the right JA, I get 0. So here I have always a positive mode, because if this is n smaller equal than -1, this will be bigger equal than 1, because the m is 0. Now, so only this can contribute, and the only one I have is the J0 for n equal to 0. So this, okay, I write down what is gamma. If this, and what this is just J0A, J0A. Okay? And good, so what is this J0A, J0A? Now this is just the quantity in the finite dimensional representation of the Lie, of the finite dimensional Lie algebra, of the zero mode representation. And if you look at it, it's precisely the definition of a Casimir. operator. I sum over the indices, I take the same element. So what comes out here is the Casimir of the representation lambda acting on lambda. Good. And good, in my convention, which is maybe slightly strange, so I write it out, the Casimir representation, the Casimir of an SU2 representation in this convention is 2LL plus 1. Okay, there's an annoying factor of 2 I have to hide somewhere. Good, so the conformal weight, delta L, sometimes I call it also HL maybe, so these are, in different literatures you will find delta or L, H pretty interchangeably, is L times L plus 1 over K plus 2 in the SU2 case, because the dual Coxeter number is 2. So that's just. And if you know the conformal weight of the highest weight state of this lambda, you will know the conformal weight of any descendant, because if you put oscillators, you will just change your conformal weight by an integer. So to be explicit, what is the conformal weight H of, okay, I put some descendants, okay, any number you like, on this lambda. It's the conformal weight of lambda, which was this Casimir lambda over 2 K plus HV, and then just the sum of the ni's. Okay, so this is just for you to recognize that once I know the conformal weight of the primary state, I know the conformal weight of everything. Yes.
Is that the only null vector?
Yes, from what I said, the question was whether this is the only null vector, or the only two null vectors. There was the stupid one and the interesting one. And the answer in this case is yes, but from what I said, it's not obvious that the answer is yes, but it's true.
Sorry, I might just have to slow, but there's 2 lines in between on the right-hand side. They are SU2 again.
Yeah, so every time there's some L somewhere, it's SU2. Every time there's a lambda, it's general. So I just want to be as concrete as possible. Good, thank you. Any other questions? Okay. So now we understand representations. So I immediately jump to the last lecture of Sylvain and talk about characters. So characters are just some way of counting how many states does a representation have. So let's recall quickly what was a character. And so here I mostly again work with SU2, but you can generalize, it's not hard. So a character, I put subscript L, is a representation, is the trace of a ML QL0 minus C over 24. ML I haven't introduced. ML is the Verma module L where I divide out by all null vectors. It's what Sylvain called R for the Virasoro algebra, RRS. Now it's labeled by L. Good, and this is the irreducible Kac-Moody representation. And I trace again over this, and the Q is e to the 2 pi I tau, where tau is the modular parameter of the torus we are on. So now suddenly we jumped from the plane to the torus. We'll see what this does. And good. So maybe recall that there were these nice conformal transformations. So if I do like this, maybe I do more general. So I can put any lambda. Now lambda is again general. It's in this set of allowed representations, which I called R. Then there was the modular T matrix, which told me how it transforms. Like so. So they transform covariantly under this T and S transformation. And T is pretty boring. I think Sylvain didn't even introduce the T because it's just a bunch of faces. But the S matrix is much more interesting. So and yes, so you have these nice modular transformation properties.
So now you just have one copy of these. You don't have a Q and a Q bar yet.
Right. I will put them. So the question is, now I have just one copy of Q. That's right. For characters, we just have one copy, and then we combine left and right, as Sylvain did, and construct a full-fledged CFT. So now this is still an amputated CFT. It's only the representations of the symmetry. Good. For these algebras, it's actually convenient to do a slight generalization, because we have two quantum numbers we can keep track of. So this keeps track of the L0 eigenvalue of any state, which we computed up there, how it looks like. But we can also keep track of the SU3 eigenvalue of J03. So you can write down some slight generalization, chi L, which now depends on two variables, z and tau. And so this z has nothing to do with the z coordinates in the complex plane we used before. It's just some auxiliary variable. And this is now the trace over the representation ml, ql0 minus c over 24. And now I put another y to the j03. And y, similarly to q, is the exponential of 2 pi I z. Okay, so if you want, this is the fugacity of that additional variable. Okay, and even with this modification, we still have nice modular transformations. Good, so maybe let's write them down. Okay, maybe this time only for SU2. So in general, if you have some bigger algebra, you could introduce such an additional variable for every Cartan generator you have. So you have rank G additional variables if you want. Good. So we still have some nice transformation properties. Now we run just over L prime here, which was bounded by K over 2. And we get back this T matrix. So, and there's Z tau. Okay, so nothing changes with T. With S, there's a slight modification. So it's only modular covariant if you want, and not slightly less nice. So the Z also transforms on the modular transformations like that. And you get an additional prefactor, which is kz squared over 2 tau. And again, you sum over those, get you S matrix. Okay, so you have an additional factor. And this k is, again, the k of the SU2. Okay, so with that, we can in principle start writing down characters of these SU2 representations. And okay, so we're sort of immediately in the hard case of Sylvain. Sylvain was in a nice position that for the Virasoro representations, he could write down the generic characters, or maybe the characters with one null vector, and they were pretty simple. There was one Dedekind eta function, which is not so complicated. But then for the doubly degenerate, it was complicated. And we are sort of immediately in the doubly degenerate case. So, but let's be brave and introduce what these are. And let's write down what those characters are for SU2. And okay, so this will be without proof. And I will tell you in a second what these thetas here are. So I just write it in terms of some other function I haven't defined yet. So, and this is theta 2, 1, z, tau, theta minus 1, 2, z, tau. Okay, so it's a quotient of these weird thetas. And before I tell you what the thetas are, I also give you an alternative form. So sometimes one is more useful, sometimes the other is more useful. So the numerator stays the same. And the denominator changes. The denominator I now write in terms of some infinite product. So I have some weird prefactor. Some of you might recognize what follows, like so. And then I have my infinite product. 1 minus q to the n, 1 minus y q to the n, and 1 minus y to the minus 1 q to the n. Good. So now let's tell you what all these things are. So here the theta k. So attention, here's k, there's k plus 2, which is a bit annoying if you want to put it on the computer. Pay attention. But this you can just put on the computer and see what it is. It's a nice thing to play around. And this is a theta function, some level k theta function, and consists of summing of all over all integers shifted by this argument m, and here you put k n squared y k n. Okay? So you see it's something you can relatively easily compute. You put it in, you expand it to whatever your order you want, and you see your character. So, but let's try to understand a bit more what's going on. So first of all, we have these two different forms. Okay, and it's very not obvious that they're the same. So here you have an infinite sum in the denominator, whereas here you have an infinite product in the denominator. So some of you might have seen this. This is just two different forms of writing Jacobi theta functions. So there's the product representation and the sum representation. And such a thing, such an identity, exists always for F and Kac-Moody algebras, and that's the Weil-Katz denominator formula. So for finite dimensional Lie algebras, you might know that there's this Weil character formula, and there is always some way of rewriting the denominator, and this is the affine analog. So, but that's just, and this has, funnily, very many applications in number theory, which I find quite nice, and all kinds of mathematics. Good, so let's try to understand what's going on and why the character should have this form. So maybe we discuss this form because it's a bit better to understand it. Good, and many terms you might recognize from Sylvain's lecture. So for instance, there's a term which goes, so let's try to understand the products first. So we have these products. And he already had them, except that he didn't have the y's. Okay, so he had one of those products because he said, okay, you can act with any number of L minus 1 times on your highest weight state. So this gives you a contribution 1 plus q plus blah, 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 just 1 over 1 minus q. You can act any time you want with m minus 2, which gives you 1 over 1 minus q squared, and so on, the product of all of them. So now we don't have the L's, we have, but we should work in terms of the J's. And we have three kinds of them. We have the J plus, the J3, and the J minus. Okay, and with any of those, we can act as many times as we want. That's why we get the three terms now. You see that one is coming without y, because it's not changing the SU2 potential, the J3 zero eigenvalue. It's not changing it, that's the J3, the action of J3s. That's the action of J pluses, because it changes the SU2 potential 1 up. And that's the action of J minuses. It takes it 1 down. Okay, so this is infinite product, even if it looks somewhat beastly, is basically the contribution to the Verma module of the free action of all oscillators you have. Okay, so now let's look at other terms. Is that clear so far? Good. So let's look a bit at the numerator. So there are these weird theta functions. Let's look just at the lowest terms. So we have this. So the lowest term you have is if you put here n equal to 0. So that has the lowest, not n equal to 0, but this integer to 0, and then n is m over 2k. So it will start with q to the m over 2k squared. Now m is 2l plus 1, and k is k plus 2. So we have to pay attention like this, and then we have to square it. So there's a 4, and this one is squared. Okay, so this is the first one. And it doesn't matter whether I put it here or here, because if I put m or minus m, it doesn't matter. So for both of them, this is the leading order term. And then it goes on. So now we have here also some y's. So this is y times kn. So again, if I put this integer to 0, my n is just m over 2k. So I get m half, and the m I have here is 2l plus 1. So I have l plus 1 if I divide by 2. Here I have this, and then I get more terms, but which lie higher in conformal weight. Okay, so now let's try to identify those terms. What happens here? Okay, so we have one term of the form L plus a half minus YL minus a half over Y half minus Y minus half. Okay, that's this part and this part together. So that's the appearing at the lowest order in conformal weight. But this is, you can rewrite because that's a geometric series. At some point you will cancel. That's just a global SU2 character. This is equal m minus L to L, y to the L, where m minus L is always integer, summing over all integers. Okay, so this is just this. So this just keeps track of my zero modes, because I can also act with my J0 minus modes, which I didn't include here in this infinite product. And at some point I stop, that's why it stops here. Okay, so now we have the zero modes and the negative modes. So we have basically everything included. What we haven't seen so far is what is the leading conformal weight, and we haven't seen how the null vectors arise. So let's look at the leading conformal weight. So what's the leading exponential of Q? So we had this from the numerator, this term here, and there we subtract out 1/8. Okay, so this you can rewrite nicely as Q to the L times L plus 1 over K plus 2. So this is missing here now a term 1 over 4K plus 2, but I can compensate for this by subtracting 3K over K plus 2 and 24 here. Okay, that's just an identity. Good, but we know what this is. So this is the conformal weight of a highest weight representation of spin L. And this here is minus C over 24. Oh, I mean, the minus is this minus. So you exactly get the prefactor you want, because remember this was the central charge we got from the Sugawara construction. Okay, so we have also exactly the right leading conformal weight. So now basically we have checked that the beginning of the character is right. And here there's an infinite sum. We just considered one term of this infinite sum. So the next term will correspond to subtracting the null vector at this level k plus 1 minus 2L. And you can, you should insert and convince yourself. It's also in the lecture notes. But these infinite terms come from subtracting the null vector with all its descendants. But then you subtract too much, because also the null vector has again a null descendant, which you should add back in. And then it goes back and forth, and you get an infinite sum, basically. So that's how the character comes about. So I hope I showed you slightly what the structure of these characters are. And it's nothing too frightening. You can just put it on a computer and expand. Okay, maybe let's take a break now and consider. Yeah. Are there any questions? So, yeah. Yes.
Give me a simple argument to see that Z also changes in the S.
Okay. The question is to give a simple argument why Z changes under S modular transformations. So one way of writing it of understanding is that Z is actually a coordinate on your torus. So now if you change your torus, the structure of your torus, also your Z, your coordinate on the torus has to transform with it. So that's the right way of transformation under that.